Okay. Can anybody tell me how to solve this? How to prove? Why? Okay. Shall I? No, I will prove it because it's not worth for homework. I prefer to give some harder questions there. Well, okay, indeed. So we have to prove that this is a group. Okay, indeed. Take A and B in special linear group. Yes, then, by definition, the determinant is equal to 1. We need to prove that A times B to the minus 1 is also there. So what does this mean? This means that we need to prove the determinant of this matrix is 1. Until now, I've just expanded definitions. I haven't done any kind of argument, logic, or something like that. Okay, how do we do that from this we get this? Yeah, but okay, but determinant of A times B minus is the determinant of A over the determinant of B. This is property of determinants. So first we get the determinant of A times the determinant of B to the minus 1, and the determinant of inverse is 1 over the determinant. And this is 1 over 1, this is 1. Okay. So some interpretations of groups are not only in some kind of algebraic structure but has some properties that is satisfied, but it originates from studies of symmetries. So I said at the morning we have a symmetric profile set, and here we have three, but also with the general linear group is a group of all invertible linear transformations. And these things with determinant 1 are volume preserving transformations. So for example, in 3D if you have some object, let's say some tetrahedron, and you apply to it a transformation with determinant 1, the volume will not change, because the determinant shows how the determinant determines volume change. There are other interesting subgroups of the general linear group. You can try. Okay, some other examples. So another example, I just stated This is the orthogonal group. ON is the group of all matrices such that its inverse is its transpose. And also SON. So this is called the orthogonal group. This is the all motions plus reflections. This is the group of all linear transformations that don't change distance. So this is a subgroup of the general linear group. And SON, these are rigid body motions. These are so this is a subgroup of the orthogonal group, which also means it's a subgroup of the big group, which is the general linear group. And these are those with determinant 1. It also can be written by the intersection of orthogonal group with the special linear. So it is orthogonal and it has determinant 1. And the general special linear. And this is the special linear. Special orthogonal. Special orthogonal. Okay, if this you can check them at home. It will be useful exercise. Now let's talk about ring-like structures. So we now further increase the number of combinations. So let R is a set plus and multiply a various plot. You must plot of functions from R. Yeah, so these are here. R is not real numbers. The real numbers are beautiful like with double line. Are binary operations. And we say that they, I don't know which distributes, maybe multiplication distributes over addition if row A, B, C, R, the have A plus B times C equals A times C plus B times C, and A times B plus C plus A times B plus A times C. So these are the two discrete flows. I think you see why I use plus and multiplication signs, because it reflects the usual operations that are property. And yeah, in most cases, it will be this way. I don't think I need to write down examples. Of course, any kind of addition and multiplication which I'm used to in real numbers, in integers, in matrices, satisfy these properties. So let me give definition of link. So let R plus 0 minus B append it's a commutative property. And so these are the elements. No, sorry, not the elements. Multiplication, the semigroup. So to remember, this means that this is associative. And plus distributes over the multiplication distributes over over addition. We say that this combined structure A plus multiplication is a ring. Okay. If I will just give some different types of things examples and then study some examples. If R has multiplicative ability, so identity if we divide by 1, so R plus is a moment. This way we say that R plus multiplication there's no 1. 0, 1, and that equals is
Why R plus dot is the number?
Ooh.
Yeah.
1.
One.
Yeah, so that's. So yeah, it has a identity element, so we can make it a moment. Then we say that this structure here is a link with unity. And if R is commutative, so if multiplication is commutative, we say that R with plus with multiplication with 0 with negation is a commutative link. And a commutative link with unity is we combine both properties. If it is both commutative and as identity, it is called commutative. It is called commutative link with unity. Commutative link with unity. And this is where link with unity. This will be the main object which we will base our theory on.
Algebraic.
Yeah.
Do we not require the inverse function of the multiplication?
No.
Okay.
If
I see.
It has unity and okay, it so always has unity, it has inverse. If it has inverse, okay, let me write down anyway. If it has unity and one which is not the answer because there is thing called trivial equal becoming zero element. But if the unit is the one it doesn't equal zero and any non-zero element is invertible, any non-zero element is invertible. We call it division link. And if it is a commutative division link, we call it a field. And there are many structures in between commutative links and fields, so non-commutative links and fields. So we have the basic structure is ring. If you are identity, we have ring between it. If we have commutativity, we have commutative ring. We can combine commutative ring between it. We can have unity and differences, but not commutativity. And we can have everything. Now I will write down the axioms. So we have A plus B plus C equals A plus B plus C. So first we have four axioms for a billion group. A plus 0 equals 0 plus 0 equals A. A plus minus A equals minus A plus A equals 0. And A plus B equals B plus A. And then we have multiplication. So A times B times C equals A times B times C. And we have two distributive properties. A times B plus C equals A times B plus A times C. And A plus B times C equals A times C plus B times C. So this is a ring. Now, if we have identity, so A times 1 equals 1 times A equals 1, this is ring continuity. If we have A times B equals B times A, we have commutative ring. If we have both, we have commutative ring between it. So I call this 1, 2, 3, 4, 5, 6, 7. So this is the 1 to 7 is the basic structure, and these are additional structures. But if we get A plus 9, so we have commutative ring continuity. Let me have 10. 10 is inverse. A times, so O and 1 is 0. A times A to the minus 1 equals A to the minus 1 times A. This is division ring. And 11, no, not 11. If we have everything, so from 1 to 7, we have always it. This is the basic structure. And if we have 8, so this is 8 plus 10. We have, if we have 8 plus 9 plus 10, then we have field. Okay. So now let's give examples. First, are the natural numbers a ring? Do they have inverses? natural numbers. So natural numbers, they are not a building group other addition. So n plus so is not a ring. Doesn't have negation, no negation. So the simplest string, okay, there are finite rings, but it's not that interesting. Yeah? The simplest string is Z. So we start with Z integers with addition, multiplication. Do they have unit? Do the integers have unity? One. So this is commutative link with unity. Link with unity. Okay, for the rest I will not try the operations because they're always the same. Sometimes there's some strange operation, in most cases they're written the same way. No, it's better to write that. Cube. It's better to write because for matrices. Q is also commutative link with unity, but it has inverses for the vertical elements. So it's a field. No, but this is not a field. Real numbers as well. The complex numbers also, I haven't mentioned them so far, but because I won't need them, but also a field. Complex. So if you want to show what this is. Have you heard about quaternions? Oh, page. Is this like that? With
Yes.
yeah, okay. And what structure they are? Okay, they are link, but do they have the identity? Yeah, the one we have, they have one. Is the multiplication commutative there? Do they have inverses? Yes, so it's this is the archetypal example of division ring. In fact, there are finite fields, but they're not finite division rings that are not fields. This is theorem of algebra. So this is division ring of quaternions. I think I spelled it correctly. This is quaternions. So they're not non-commutative. Square matrices under, let's say, it doesn't matter. No, it doesn't matter. But let's say real numbers with and bigger than 1 because 1. Does every non-zero matrix has inverse? No, only the determinant is non-zero, but you can have a non-zero matrix which has zero determinant. So it's not commutative. So it's linked with unity, yeah. With unity. So not commutative, not inverses. Not inverses. In general. And some final example. Two z's, so even numbers. If it's n bigger than 1 equals, so n bigger than 1, and we take n z. So before we prove that they are group, if we add or subtract two numbers divisible by n, they are also divisible. The result is also divisible. Right? But if we multiply two numbers divisible by n, the result is also divisible by n. So they form the thing called subring, which I didn't define, but the idea is similar to subgroups. So we have addition, multiplication, we have zero, and we have subtraction. But we don't have identity because we erase one. So this is commutative ring without unity. Without unity. Without unity. So you see all these properties from 8 to 10. One of them doesn't force the other one. Okay. Oh, let me give some other example here. Because I have some time, but I don't want to start linear algebra, so modular theory. So I will prove some important necessary. So what is each so let's give a set every link. No, okay, let's fix. It's addition. I'll care only about this because it is. So, addition, multiplication, it's different between it. Then define on the set. Define on the set. So the set R to the power of x is the set of all functions from x to r. So it is the set of all functions from x to r. Addition by, so addition, I call it, usually let's use the same symbol plus, but for this particular introduction I will use some kind of distinction plus 3 from Rx, Rx, okay, Rx by Rx, Rx by so so we have as follows. Okay, I will define additional multiplication in a symbol and multiplication. And Rx as follows. For any x, f and g, for any functions f, g, and Rx, and any x1, x2. So we take two functions and we have to multiply and add them. So we have to show how to, so this is like that sum of functions applied someone likes. No, I have two functions and add them. How do I apply them at x? If I know f of g, how do I find f plus g?
X plus 3x.
Yeah, f of x plus g of x. And f times g of x is again f x multiplied by gx. Okay, make this practice here. So this is how we define. So this is the definition. Then we claim that the I said before, usually if you have only multiplication, you have unique. I said before, usually if you have only multiplication, you have unique. In a monolith group, if you have the binary operation, other operations, it can form a unity. It can form a unity. Absolutely. With unity. We just so x we have plus and multiplication, and I have also this operation here. Okay, so what is the zero element? What's the zero function? Okay, zero function is the function that to x maps 0. I don't know if no, you don't like this. Defined by is equal 0, 1 is defined by so these are the constant functions. And x and x of x. And the negation minus f of x is defined by minus f of x. So this is the so-called tilde operation, and so we take the negation of function, which when we map to x, we first take function of x and then the negation. So this operation is for the ring, and this is for the function ring. Again, for any f in R x and x in x. There are 9 tips to check the trivial. I just check, I don't know, one. So idea proof. For example, check associativity. So, for example, if you have numbers and you have some, this rule to set to the real numbers can be added and so on, and usually we restrict to smooth functions, but then again, the same logic follows. But let's say associativity of so take f, g, h in f to the power of x and some one of x in x cubed. Then f plus g plus h of x. So this is the first thing. Other thing is with different brackets. You need to check that equal. Well, this is f of x plus g plus h of x. And this is f of x plus g of x plus h of x. Right here. And the other side is the same with different brackets. So here, the first part, we just at the beginning, we copy it. The second, apply h of x. And then expand the first part as well. So this is f of x plus h of x. And these two things, they are equal because we have associativity in the initial ring. These are equal. Since class is equal to and okay, so we finished here. I'll just give some problems. Anybody please? Sorry. So this is just playing with the definition. There is not any argument. You just need to take function and expand and follow the definitions. Okay. Let me do some progress. I think you already know that, but you don't know that you know it, because you haven't done a lot of, you have done a lot of, you have done a lot of calculations with functions, additions, multiplication of functions, and but not in that abstract way. Maybe you usually put some argument here x, but you can do all the implementation without the argument, only with the functions themselves. Okay, so first here is the proof. The proof for that Rx is equal to two. Let's go back to groups. So on field, define the operation start so we have this operation by A star B equals A plus B plus A times B. Prove that for AI rational numbers. So prove that it is associative and has unity. So it is a monolith. And find the group of units. Find the group of units. So this is an example of unorthodox operation. It's not addition, not multiplication, but some combination of them. But it turns out that this operation makes rational numbers a monolith. And if you find the invertible element, you find the group of units. Some more involved example. Let's have k be a positive real number. Define star in from the interval minus k r by sorry. So we take two elements in this interval by a star b. This is standard problem. Check this. A plus b over 1 plus k a b. I think just this one. Yeah. Proof it is proof that so first you need to prove that the operation goes in minus kk. That if a and b are minus kk, A star B is also minus Q3. So it's closed. It doesn't go outside. And it is a group. It is a group. And so it's star determines, I don't know, determines a group. So you need to find the units and the inverses, and finally, 1 and 4. On, let's say, R squared, define no, I'm not sure. Okay, define addition by so addition is defined as follows: A B plus C D is A C D and A B times C D A B times C D equals A times C and AB plus BC. Yes. For ABC real numbers. And this is the this ring. Our commutative matrix is and tell me whether it is easy to fluid. Okay, we can finish. I just forgot to say that for the previous example of functions, if we start with the commutative link with unity, the set of functions is also commutative link with unity. But if the initial set is transferred, but inverse elements are not preserved. Okay, let's finish. Okay. It's just that I defined, so these symbols here, they're new symbols. I defined this operation by that. Because I have multiplication and addition, and I need new symbols. Like here, this is a new symbol, and this is a new symbol. Okay, any other questions?